Welcome to the class of matrix solvers. This is the very first class of this course. A number of engineering and physical systems as well as systems involving social sciences like economics deal with large number of equations. Equations which are generated from systems which deal with a very huge number of variables, and these equations are often represented as matrix equations, and in many times we need very fast efficient solution of the matrix equations, and also there are situations when you do not need solutions of the systems of the equations, rather we need to see how the system behaves just by looking into the system of equations. So, in this class we will try to cover a large group of solvers which can address the system of equations, and we will also see the cases when these equation systems are solvable, what are the other issues with the equation systems, and how the equation system tells about coupling between the behavior of different parameters. So, today's class is on introduction to matrix algebra. This is a very elementary level class. We will have discussion on the definitions, notations, and few of the elementary matrix operations. The main intention behind this class is that getting acquainted with the right conventions, so that throughout the entire syllabus or all the classes all of us be in the same page on the definitions and notations used for different matrix operations. But before going into that, quickly let us see what this course will cover. So, this course will primarily discuss on these issues. First is solvability of matrix equations, in which cases the matrix equation has an unique solution, and there are multiple cases where the solution will not have unique solutions. One case is that the solution will not have any solution, the equation systems will not have any solutions, or we will call that to be a inconsistent system of equation, and there can be another case when infinite solutions exist for given equation system, and usually these cases arise when number of variables or number of independent variables is not equal to the number of equations given to us. And then we will look into different types of solvers. One is the direct solver and another is iterative solvers. Direct solvers, that as the name suggests, directly solves the matrix equation, gives us what is the solution in terms of values of different variables, whereas iterative solvers start with a guess value and then does an iterative technique using the matrix itself to update the guess value, so that it finally converges to a right solution. The main important thing with iterative solvers is that what is the rate of convergence of these solvers, and there are pros and cons behind each solvers, not only behind choosing direct solver or iterative solver, also in choosing different types of solvers within the general class iterative solvers. So, we will see what are the issues with different type of matrix solvers, and we will also see how to implement these solvers in softwares, because for a large equation system in today's world, many a time we solve million by million, 100 million by 100 million, even billion by billion matrices, and when we are solving these large matrix systems, we use efficient softwares which are implemented over modern computer architectures. And one goal of this class is also to look into implementation of these matrix solvers in different softwares and what are the issues with that. Also, we will discuss how these matrix equations are obtained from different physical system analysis. And knowing that this equation which you are solving is coming from analysis of a physical system, how the behavior of the physical system can be utilized while devising an efficient matrix solver, or usually these solvers in number of cases there will be where these solvers are coming as a projection of differential equations. When computers cannot solve differential equations, computers do not understand what is derivative. So, when we try to solve it use differential equations using computer, we convert them to difference equations, and these are multi degree of freedom difference equations which come as matrix equations. So, if we can use the very basic nature of those differential equations to solve the projected matrix equation. So, these things we will also discuss at different parts of this class. The main two textbook will follow this class is one is linear algebra and its application by Professor Gilbert Strang. This is one of the very extremely cited and referred textbook in linear algebra and matrix calculations, and this book will primarily use to see the behavior of different matrices and about different matrix operations, and to also to look into the cases when a matrix equation has unique solution or has infinite solutions, and also to look into the direct solvers. For the iterative solvers, we will mostly use the second book, which is Professor Youssef Saad's Iterative Methods for Sparse Linear Systems. Its second edition was published by CM. First edition is already available online in Professor Saad's web page, and this equation will deal with number of iterative solvers, their issues, the algorithms will probably directly use from Youssef Saad's book on these solvers. So, now we move to our main discussion, and today's discussion is on elementary matrix algebra. The first question comes, what is a matrix? And we can see matrix is a regular array of numbers or symbols or expressions, and so as it is a array of numbers and symbols and expressions, it should have two components. It is a rectangular array. So, it should have a something in a horizontal direction as well as something in a vertical direction. The horizontal arrays within a matrix are called its rows, and the vertical arrays are called its columns. So, if we look into few example matrices, there are three matrices shown here, and entry of the matrix or each element of the matrix can be integer, can be an irrational number, can be any real number, can be complex number. Also there are cases where these entries are logical entries, or we can have Boolean matrices. Now, if we look into each matrix, it is, as I said, it is a rectangular array of numbers, and we can see both vertical arrays which we call columns, and we will also see horizontal arrays which we call rows. Now, rows and columns are also matrices, even a single number can also be thought of a matrix. Now, as I said, entries of a matrix can be any type of numbers, it can be real, complex, integer, imaginary, irrational, and we may have Boolean matrices also. So, a matrix is usually given as a rectangular array, where the entries can be anything which is shown as a matrix, which has number of entries inside it as directed along rows and columns. So, it has total 1, 2, 3, 4 n number of columns and 1, 2, 3, 4 m number of rows. So, this, if we look into this matrix, there are total m rows, 1, 2, 3 m rows and 1, 2, 3 n columns, and inside this matrix any number can be identified by its position according to row and column. For example, this number goes to the second row, this number goes to second row, and 1, 2, 3 third column. So, each entry inside the matrix will have a unique identification based on its row and column, and we can see this matrix has m rows and n columns, and the matrix A is said to have an order m into n, and is usually written when we need to show its order also A and in subscripts m into n, and each element in A is identified by its row and column index. So, Aij is an element, small aij is an element of the matrix capital A, small aij is an element of the matrix capital A with ith row and jth column. Okay, this is how an element inside the matrix is defined and the order of the matrix is also defined. Now, one dimensional matrix is called a vector. That means a row is also a vector. If m is equal to 1, the row will become a vector, for like 1, 2, 3, 4 arranged in one horizontal array is a vector, and if n is equal to 1, that is also a vertical array which is called a column vector. So, there are two types of vectors, usually row vectors and column vector, and a matrix which has only one entries 1 into 1, that is also a rectangular arrangement if we see, and that is called a scalar. Any vector can be represented by a matrix of real numbers. That means, when we talk about a vector, for example, say we talk about 2i plus 5j, which is a vector. So, in x direction there is 2 units, in y direction there are 5 units, and we can write it as 2 and 5, these two numbers. Similarly, a three dimensional vector can be written as a column of row size 3, or the column with or column matrix with order 3 into 1. There are 3 rows and 1 column. So, instead of 2D and 3D, because we are dealing with a very large system of equations in several times, we think of higher dimensional matrices, and higher dimensional space is not a physical space, but we imagine the physical space to have more and more dimensions after the third dimension, which of course, you cannot easily visualize, but we can think of it. So, for example, I have x, y, z and I think of another coordinate zeta, that gives me a 4 dimensional space. Similarly, a higher dimensional vector can also be represented as a column matrix. It will have 1, 2, 3, 4, 5, 6, 6 entries. So, this is a in a 6 dimensional space, a vector in a 6 dimensional space, and several times we have to work with higher dimensional spaces in matrix algebra. So, we start looking into some of the important matrices. Basically, we look into the definitions of these things. So, when the notation is used, we will figure out that actually this type of matrix has been discussed. So, one is a 0 matrix, a matrix which has all elements 0, and it can be matrix of any order, like for example, if we write by O 2 into 2, that will be a 0 matrix which has 0 0 0 0, which is of 2 into 2. Similarly, if we write O 1 into 4, that will be this 1 means it has 1 row. So, it is a row vector with 4 columns. So, again there are 4 zeros. In any space, a vector, a 0 vector or a 0 especially a 0 vector in any space will denote the origin, where all the coordinates are 0. So, next is not a 0 vector, 0 matrix, rather a matrix where most of the elements are 0, sorry, most of the elements are not non-zero, where there is I am sorry, there is a mistake here. So, we should make it a vector where most of the elements are 0. A sparse matrix is a matrix in which most of the elements are 0. For example, if we think of a matrix, say 1 2 0 0 0 0 0 1 0 0 0 0 0 1 2, like this, like there are 15 entries 3 into 5. So, this matrix has an order which is 3 into 5. Among these 15 entries, only 5 are non-zero. So, these are called sparse matrix, where most of the elements are 0, and these type of matrices are often arise while we are solving physical systems. So, physical systems analysis often give sparse matrices, and we will see sparse matrices in say, as a class of matrix coming from problems in computational mechanics, especially as example, and there are specific matrix solving algorithms which are designed for sparse matrices because of their huge applicability. And as this is a little qualitative definition that most of the elements are 0. So, quantitative definition also comes on sparsity, that is the total number of non-zero elements divided by total number of elements. For example, in this particular application, total number of elements is 5 into 3 15 and non-zero numbers are 5. So, sparsity will be 5 by 15. Sparsity should be very low in order to have a sparse matrix. And if the non-zero numbers are configured to a diagonal band, then we call it to be a banded matrix. For example, if we have a matrix like this 1 2 1 2 0 0 0 1 2 0 0 0 1 2 0 0 0 1. So, all the non-zero numbers are distributed along a band near the diagonal, and this is called a banded matrix. There is a dense matrix where opposite to sparse matrix most of the elements are 0 and density will be 1 minus sparsity. So, number of 0 values divided by total number of 0 elements divided by total number of elements. A square matrix is where number of rows is equal to number of columns, and which is in a square matrix the entries with same row and column index are called the diagonal entries. So, if we see an example, for example, in this matrix 1 2 3 4, the entries with I is equal to 1 and j is equal to 1, I is equal to 2 and j is equal to 2 are the diagonal entries. Similarly, if we take a 3 into 3 matrix, say let 4 5 6 7 8 9 10 11 12, the diagonal entries are identified as 4 8 12. So, which has same row and column index, and if a square matrix has all the off diagonal non diagonal entries 0, we call it to be the diagonal matrix. So, only the diagonal values are non-zero or may be non-zero, there can be some zeros also, but all the off diagonal values should be 0. So, a matrix like this 1 0 0 0 1 0 0 0 1 is a diagonal matrix, or a matrix like 5 0 0 root 3 is also a diagonal matrix, where only the diagonals are non-zero. So, a question comes whether a diagonal matrix is a sparse matrix or not, and of course, because most of the elements are 0 here, only very few elements are non-zero, and if we see the definition of the sparse matrix, that if we see the definition of the sparse matrix where most of the elements are 0. So, if we have anything greater than a 2 by 2 ordered matrix, will have the diagonals only non-zero, off diagonals are much more than the diagonal terms, and therefore, it should be a sparse matrix. Rectangular matrices, so we are discussing only about square matrices. They are rectangular matrices, in which case in cases they follow the definition that the terms with different row and column indexes are 0 are called matrices with rectangular diagonal form, and an example can be a rectangular matrix 1 0 0 0 2 0 0 0 3 and 0 0 0. So, any this matrix has number of rows more than number of column. So, any row which is beyond than the maximum column ID should have all zeros for this form. Similarly, if we have a say 2 into 3 matrix 1 0 0 0 2 0, this is also of diagonal form, and any column which is more than maximum row number should have all 0 entries here. So, these are few of these definitions. We will see few more. We will see some of the important more important matrices. One is a diagonal matrix must be a square matrix. If diagonal entries are 1, it is called an identity matrix, and identity matrices are generally denoted by I. For example, I 2 into 2 is 1 0 0 1, I 4 into 4 is equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. And now, there is a restriction on what type of entries will these matrices have, and these will only have integers, because 1 is an integer in their diagonals. We cannot have complex matrices or imaginary entries in a identity matrix. There are some other definitions. Upper triangular matrix, let me clear this. Upper triangular matrix is a matrix for which any term which has a row index more than column index is 0, and it looks like a triangle, and it is also for a square matrix. So, if we have, for example, if we have a 3 by 3 matrix, one, 2, 3, this is first row and first row and column is 1 2 3. So, this is non-zero. This is second row, the column number is 1. So, this is 0, maybe 2 4, and this is 0 0 5. This is a what is called an upper triangular matrix. It can be something like this also, 1 2 3 4. Again, this is first row. So, first column onwards everything is non-zero, but second row first column is 0, 1 2 3 0 0 1 2 0 0 1, maybe root of 3. It can have any entry in that sense, and the lower triangular matrix is the opposite one. So, we can see that the matrix actually the numbers given in the matrix, sorry, this is 0, I am sorry, this is also 0. The non-zero numbers given in the matrix forms a triangular shape, and a lower triangular matrix is just the opposite. It has where the column index is more than row index, it will be 0. So, 1 0 0 2 3 0 0 4. Interestingly, it is mandatory that these terms, the terms with column ID greater than row ID, or in case of lower triangular matrix like these terms, or in case of upper triangular matrix row ID greater than column ID has to be 0, but any of the other terms or many of the other terms can also be 0. A sparse matrix can have lower triangular and upper triangular form in that sense. We go to upper triangular and lower triangular form of rectangular matrices. A matrix which is not a square matrix, if it follows the definition of upper triangular or lower triangular, that is row ID greater than column ID, it is 0, then it is called upper triangular. Column ID greater than row ID, all the terms are 0, it is called lower triangular. So, there can be few examples of that. So, this is a rectangular matrix which is of upper triangular form, this is a rectangular matrix which is of lower triangular form. They are not called upper triangular and lower triangular matrix, they are called rectangular matrices of form of upper triangular form or lower triangular form. In many cases, we see matrices, square matrices, which are not of triangular form, but of nearly triangular form. or nearly triangular form. That means, they follow this rule very nearly, but they exactly do not follow this rule. Maybe one more band or one more term near after the diagonal or before the diagonal is still non-zero, and we call them to be Heisenberg matrices. His upper or lower Heisenberg matrix is that A I j is equal to 0 for I greater than j plus 1. That means, we can allow still one more row to be term with one more row index to be non-zero, which is after the column index, and similarly we can have lower Heisenberg form. And these Heisenberg matrices will come when we will discuss about one of the very recent developments in matrix solvers, which is called Krylov space solvers. Interestingly, matrix solvers has been developed over last more than 2 decades, more than 2 centuries. Earliest matrix solver which we will discuss is was obtained in 1st century writing of Chinese mathematicians. However, those solvers are not discarded yet, they are not obsolete. We use those solvers heavily in different type of calculations, even in very modern computer programs also. Anyway, so one of the recent developments are in last decade, which are called Krylov space methods, and they used not last decade, at the end of last century 1990s, and they use Heisenberg matrices, which is nearly triangular matrix. The basic matrix operations, come to it. One is equality. Two matrices are called equal when they have equal order, and each term with a particular row column index is same with the similar corresponding row column index in the other matrix, and then we called if A I j is equal to B I j and A and B have same order, then we call for all I j we called A is equal to B. Two matrices can be added and subtracted if they have same order, and each term of one matrix, each I j index term of one matrix is added with the similar I j index term of the other matrix to give the resultant matrix. And similarly, subtraction between, and then we call A plus B is equal to C. Similarly, subtraction is also defined. If I multiply a matrix by a scalar, all the terms inside the matrix are multiplied by that scalar. And a very important operation is matrix multiplication. When we multiply two matrices, then and get a resultant matrix, the matrix multiplication is defined as, is only defined when rank order of one matrix and order of the other matrix will have something common, that is the number of rows of number of columns of the first matrix is equal to number of rows of the other matrix. And that why? Because the resultant matrix will have one term which is summation of each terms of one row of the first matrix multiplied with each term of one particular column of that matrix, and then we called A B is equal to C. And interestingly, the order of C will come from the order of A and B. The number of rows of C will be number of rows of A, number of columns of C will be number of columns of B. And we can see a quick example. For example, I have 1, 2, 3, 4, 5, 6, which is 2 into 3 multiplied with 7, 8, 9, 10, 11, 12, which is 3 into 2. I will get something which is 2 into 2, and each term here, this is 1 into 7 plus 2 into 8 plus 3 into 9, which will give me 50. This is 1 into 10 plus 2 into 11 plus 3 into 12, which will give me 68. This is 4 into 7 plus 5 into 8 plus 6 into 9, which will give me 122, and this is 4 into 10 plus 5 into 11 plus 6 into 12, this give me 167. So, this is how matrix multiplication is defined, and we use matrix multiplication in there are plethora of applications in matrix multiplication in linear algebra courses. Now, a matrix multiplied by a column vector, just if we look into their indices, gives us a column vector. A small simple and a row vector multiplied by a matrix gives us a row vector. So, the order of multiplication is important, as the as the number of columns of the pre-multiplier has to match with the number of columns of the post-multiplier. A matrix will be post-multiplied by a column, where a matrix has to be pre-multiplied by a row. And and a row vector multiplied by a column vector gives a scalar, but the opposite, a column vector post multiplied by row vector will give a matrix of m into n order. A square matrix can be multiplied to itself. A row vector cannot be multiplied to a row vector, because the order in terms of pre-multipliers column and post-multipliers row do not match. Similarly, a column vector cannot be multiplied to a column vector itself. A square matrix can be multiplied to itself because it has same order. This is this should be m into n. This will be m into m, as this is a square matrix. So, as this is a square matrix, this will be m into m, the orders are same. As the number of row is now equal to number of column, it can be multiplied to itself. However, when we multiply it, we see that this is not squaring of each term, rather it is something different. Probably a better squaring of the terms can be obtained if I multiply a square matrix with rotating the square matrix in terms of row and column. For example, A B into C D is multiplied with the matrix A B, is the row is changed as a column here, and we get product as a square plus b square, c square plus d square. Interestingly, in the product matrix we see that the off diagonal terms are equal, and this is an interesting class of matrix when we see similar off diagonal terms, and we call them to be symmetric matrices. And also, when row and columns are changed of a matrix, rows has become columns and columns have become rows, these matrix like this, the first matrix and second matrix, they are called their transposes. So, these are some of the matrix operations. In next class we will see some more matrix operations and definition of some more important matrices. Thank you.